Hi, it's time for another math easy solution. Today I'm going to go over further into infinite sequences and series, and this time go over formulas for the remainder term in Taylor series. And this is a follow-up from my earlier video on Taylor and Maclaurin series, and I alluded to that in that video as well. So just a quick note, if you don't have time to watch this whole video, you can play this video at a faster speed over here. Here's some recommendations, and also you can download and read the notes. Link will be in the description below, as well as viewing these notes on Steam it in article format, #GetOnSteam, and also the link will be in the description below. And also you can watch the video in parts, and so on. And as always, here's a calculus book reference that I use. So note that I mainly follow along the following calculus book, and this is Calculus Early Transcendental 6th edition by James Stewart. And in this particular video, this is part of the additional topics section of their website. It's not included in the book. Formulas for the remainder term in Taylor series. And here's a link to stewartcalculus.com. And also here's an archive of this link there, and they're both the PDF downloads of this additional topics for this remainder series. And also I've included a local PDF download that is on my OneDrive. If in case these two links aren't working, or any one of those aren't working, you could just check on my local download. Alright, so let's continue further and now look at topics to cover. I'm going to go over a quick recap on Taylor and Maclaurin series from my earlier video. Then I'm going to go over formulas for the remainder term in Taylor series. And then Theorem 1, this is dealing with the integral form of the remainder term. And then go over example 1 with it. And this is solving a sine of x. Yeah, as a Taylor series, and then using this remainder term formula. And then in that example, I'm also going to go over the absolute value integral property. It's a video I should have done years ago, but I'll prove it in this particular video. So then go over also Lagrange's form of the remainder term, and then go over Theorem 2, which is the weighted mean value theorem for integrals, and we're going to use that to prove Theorem 3, which is Lagrange's form of the remainder term. Then I'll then go over example 2, which is also going over sine of x and showing how you can get the remainder term using this method instead. And then last I'm going to go over example 3, which is x to the power of 1/3, or this is the cube root x, like that. Get rated as that, or stated as that. So now let's continue further and do a quick recap on Taylor and Maclaurin series. Alright, so first a quick recap from my earlier video on Taylor series. So here's a link to the Steamed one, and I just took screenshots from my calculus book. So theorem, if f has a power series representation or expansion at a, that is, if we have f of x equals to the summation n equals 0 to infinity cn times x minus a to the power of n, and this is the where absolute value of x minus a is less than r, which is the radius of convergence, then its coefficients are given by the formula Cn, or C sub n equals to the nth derivative f of n of a divided by n prime. I mean n factorial, not n prime. Yes, divided by n factorial. And then going for this, a Taylor series of the function f at a, or about a, or centered at a, when we just plug in this these coefficients Cn inside, and expanded, we have fx equals to summation n equals 0 to infinity of the nth derivative at a divided by n factorial times x minus a to the power of n. And this just equals to f of a plus f prime of a divided by 1 factorial times x minus a, then plus f double prime of a divided by 2 factorial times x minus a to the power of 2, then plus the third derivative, and so on. Yeah, this third derivative at a divided by 3 prime times x minus a cubed, and so on. Keeps going on and on. And the Maclaurin series is a Taylor series with a equals 0. So when you just plug in a equals 0, you just plug in there. Yeah, we just replace a with this entire thing there. Yeah, we replace just the a with 0. So there's zeros everywhere there, and so on. So that's just used, or arises very often, so it has its own unique name, Maclaurin series. And then go over further, and as I went over in that video, basically we went over and stated that a function is equal to the sum of its Taylor series if the limit of the remainder approaches 0, and is a theorem. So if fx equals to the Taylor series plus a remainder r sub n of x, where Tn is the nth degree Taylor polynomial of f at a, and the limit as n approaches infinity of r sub n of x, so the remainder, is equal to 0, and it goes to infinity for this absolute value of x minus a is less than the capital R, which is the radius of convergence. then f is equal to the sum of its Taylor series on the interval this absolute value of x minus a is less than the radius of convergence r. And going further, so Taylor's inequality is useful in finding the limit of the remainder. So this is how we dealt with the remainder in an earlier video, used Taylor's inequality. And in this video, I'm going to go over alternatives to Taylor's inequality. So with Taylor's inequality, if the absolute value of the nth plus 1 or the n plus 1 derivative of x is less than or equal to m, for the absolute value of x minus a is less than or equal to d, then the remainder r sub n of x of the Taylor series satisfies this inequality. So if we have this scenario there, this inequality, and this is the absolute value of r n of x is less than or equal to capital M divided by n plus 1 factorial times x minus a to the power of n plus 1, and this is for this domain there. Absolute value of x minus a is less than or equal to d. And this is essentially saying we're just this remainder is going to be less than the next Taylor term. So because you see this n plus 1 factorial is x minus a power of n plus 1, whereas if you look at this factorial right here, of this Taylor series, we just have this n factorial times x minus a power of n there. The only difference is this one is replaced with capital M, and it's stating that the next term is going to be less than or equal to it if this scenario is true. And for this domain where this scenario with this derivative is less than or equal to m, for this domain where absolute value of x minus a is less than or equal to d. So yes, very fascinating. So I also alluded to alternatives to Taylor's inequality, which I'll be going over in this video, and this is these are first came up in my last video, as I stated here. So as alternatives to Taylor's inequality, we have the following formulas for the remainder term. If the n plus 1 derivative is continuous on an interval I and x is an element of I, then what we have is the remainder r sub n of x equals to 1 divided by n factorial times the integral from a to x times x minus t to the power of n times by f to the power of n plus the n plus 1 derivative of t and then dt there. And this is called the integral form of the remainder term. And another formula called Lagrange's form of the remainder term states that there is a number z, but in this video I'm going to go over it's going to be c. But anyway, so z here between x and a such that the remainder r sub n of x equals to fn plus 1 of z. It's hard to keep stating this in exact accurate terminology. So this is the n plus 1 derivative of f of z, and then this is divided by n plus 1 factorial, and then it's times by x minus a to the power of n plus 1, like that. And this version is an extension of the mean value theorem, which is the case n equals to 0 there, and I'll cover this later in this video. So proofs of these formulas together with discussions of how to use them to solve the examples of sections 11.10 and 11.11 are given in the website stewartcalculus.com, and click on additional topics and then on formulas for the remainder term in Taylor series, and that's how I got the PDF. So anyways, and that's what I'm going to be doing right now. Alright, so now let's take a look at formulas for the remainder term in Taylor series. So in my earlier video recapped above, we considered functions f with derivatives of all orders, or you can continuously take the derivatives, and that is what we get with power series, and their Taylor series. And their Taylor series is given by like this, the summation up to infinity from n equals to 0, a starting point, and then the nth derivative, f of a, like that, divided by, this is going to be n factorial, and this is going to be x minus a. So this is the Taylor series, x minus a to the power of n. Alright, going further, so the nth partial sum of this Taylor series is the nth degree Taylor polynomial of f at a, and we could write this as Tn of x. So instead of going to infinity, we're going to go all the way up to n, like that. This is going to equal to, well, the first one's going to be at this is the 0th derivative, or just f of a, like that. And then we plug in, n equals 0 above here. This just vanishes, becomes 1, and 0 factorial is just 1. So f of, this is f of a, like that. And then plus the first derivative, f prime of a, when you plug in n equals 1. And then divided by 1 factorial times by x minus a, power of 1. The next term is going to be f double prime of a over 2 factorial. This is going to be x minus a squared. And it's going to keep going on and on, dot plus dot dot dot, all the way up to, and we'll just write this as the nth derivative, fn of a, divide this by n factorial. Here's going to be x minus a divided by n. Yeah, so now that we have this partial sum of this Taylor series, or this nth degree Taylor polynomial of f at a, we can write now, yes, we could write f of x. So let's say f of x is equal to the partial sum, if we set it equal to this Taylor series, or this Taylor polynomial, and then plus a remainder. So we're going to approximate it by a Taylor polynomial, so then we're going to have Rn of x like that. And again, where R sub n of x is the remainder of the Taylor series. So now we know that, we know that if, we know that f is equal to, or if fx equal to the sum of its Taylor series on the interval where the Taylor series converges, which is the absolute value of x minus a is less than r, where r is the radius of convergence. We can show that the limit, or this is true if we can show, so if we can show that the limit as n approaches infinity of r sub n of x is equal to 0. So if we can show that this remainder goes to 0 as n goes infinitely large, and again this is for this domain, this absolute value of x, absolute value of x minus a is less than radius of convergence r. So here we derive formulas for the remainder term r sub n of x. The first such formula involves an integral, and this is going to be called Theorem 1 integral. Theorem 1 integral form of the remainder term. So if f or the n plus 1 derivative of f is continuous on an open interval I that contains a and x is in I, then, or in other words, x and a are inside this open interval I, then what we could do is write the remainder r sub n of x is equal to, so there's a theorem which I'll prove, so equals to 1 divided by n factorial, like this. And this is going to be integral from a to x of x minus t. And this is going to be to the power of n times by the n plus 1 derivative of f of t dt, like that. Alright, so now to prove this theorem, we could use mathematical induction, and this is referenced below from my earlier video, and so here is a link to that, and here's a screenshot from my calculus book, just because it's more concise as usual. So mathematical induction, in proving statements that involve a positive integer n, it is frequently helpful to use the following principle. Principle of mathematical induction. So let S sub n be a statement about the positive integer n. Suppose that we have S1 is true, and also we have S sub k plus 1 is true whenever sk is true. Then Sn is true for all positive integers n, because if sk plus 1 is true whenever sk is true, this means if S1 is true, that means sk plus 1, so that's going to be S1 plus 1 is 2. So S2 is true. And if S2 is true, S3 is true, and if S3 is true, S4 is true, and so on, then Sn is true for all positive integers n. This is reasonable because since S1 is true, it follows from condition 2 with k equals 1 that S2 is true. Then using condition 2 with k equals 2, we see that S3 is true. Again, using condition 2, this time with k equals 3, we have that S4 is true. This procedure can be followed indefinitely. So for our case, for n equals to 1, let's just scroll up here. So we have here r sub n of x, or r n of x, equals to 1 divided by n factorial. Times by integral from 8x of x minus t to the power of n, and then times by f of, this is the n plus 1 derivative of t dt. And also we know that here f of x equals to tn x plus rn. So we can just move this tn, or this Taylor polynomial, to the left side and have rn. In our case, r1. So let's just go over here. So for n equals 1, we have, well, we know r1 is going to be, let's just use this formula first. So this is r1, and then move this t1 for n equals 1 over to the other side. So this is going to be r1 is equal to f of x minus t1 of x. So the first Taylor polynomial, or t1 of x. And for completeness, I'm just going to write this as, this is going to be f of x, and it's going to be minus, let's just write this in summation format, just to get used to this. So n equals 1, I mean n equals 0 up to n equals 1. up to 1 of this is going to be f n. This is, just remember what this is. This is a, nth derivative at a of f, or of f of a. And it's going to be n factorial, and this is going to be x minus a power of n. And for the first one, r equals 1, or the n equals 1 here, we're just going to have fx minus, when we plug in 0, that's just going to be our f of, so f of 0th derivative is just f, like that, just by convention. And then these ones vanish, it goes to 1, 0 factorial is 1, etc. So this is going to be f of a minus, and then the next term is going to be f prime, the first derivative at a, divided by 1 factorial, and that's just going to be just divided by 1, just leave it, times by x minus a, just move this dot, times by x minus a to the power of 1, just leave that. Yeah, now that we have this right here, this is what r sub 1 is. We need to show that is equal to this right here in this theorem, so this right side of it. And so, and the integral in the theorem is, well, we'll just write this as, write the full thing out, 1 over n factorial to the integral times by integral of a to the x. That's just this right here, a to the x, and like that, x. And then this is a to the x, this is going to be x minus t power of n, and then this is going to be f n plus 1, if I recall that. Yeah, so fn plus 1 of t dt. And now what we're going to do is we're going to take this, and this is going to be at n equals to 1, and then plug that inside. So we're just going to have 1 divided by 1 factorial, it's going to be 1. This is going to be a to the x minus t power of 1, which is going to be x minus t. And this one here is going to be, well, the first derivative. I mean, it's the second derivative. When you plug in n equals 1, that's going to be the second derivative, f double prime of t dt, like that. And now to evaluate this integral, we can integrate by parts, and as a reference from my earlier video below, I haven't done this by parts in a while. But anyways, let's just reference this over here just to get a recap. So the integration by parts, every differentiation rule has a corresponding integration rule. For instance, the substitution rule for integration corresponds to the chain rule for differentiation. The rule that corresponds to the product rule for differentiation is called the rule for integration by parts. The product rule states that if f and g are differentiable functions, then the derivative of d over dx of f of x times g of x is equal to fx times g prime of x plus g of x times f prime of x. So remember, that's the product rule for derivatives. And now in the notation for indefinite integrals, this equation becomes, we just take the integral on both sides, and it's going to be, this is going to equal 2. So this part right here is going to be integral of f of x times g prime of x plus g of x times f prime of x dx equals f of x times g of x. Or you could write this, separate this integral out, so we'll have two integrals, and where this just equals fx g of x like that. So this is going to be equal to, so the integral of f of x times g prime of x dx plus integral of g of x times f prime of x dx equals f of x times g of x. And or we can rearrange this equation as follows, and this is going to be integral of f of x times g prime of x dx equals to f of x times g of x minus integral of g of x times f prime of x dx. And notice all we're doing is just changing which one's the derivative, which one's not. So this can be f g prime, and then this can be f times equals to f times g, and this is going to be minus integral of g times f prime. So it goes from g prime to f prime now. And formula 1 is called the formula for integration by parts. It is perhaps easier to remember in the following notation. So let u equals f of x and v equals g of x. Then the differentials are du equals to f prime of x dx and dv equals to g prime of x dx. So by the substitution rule, the formula for integration by parts becomes integral of u dv equals uv minus v du. So yes, just rearrange it like that. And also, lastly, if we combine the formula for integration by parts with part 2 of the fundamental theorem of calculus, that's for definite integrals. This one's indefinite. Definite just means you're getting exact values from a to b, etc. So we can evaluate definite integrals by parts, evaluating both sides of formula 1 between a and b, assuming f prime and g prime are continuous, and using the fundamental theorem, we obtain integral from a to b of f of x. F of x times g prime of x dx equals to f of x f of x times g of x, and this is evaluated from a to b, minus integral of a to b, integral from a to b of g of x times f of x, f prime of x dx. And also note the fundamental theorem of calculus for reference. And here's the quick recap. So the fundamental theorem of calculus part 1, if f is continuous on the closed interval a and b, then the function g defined by g of x equals the integral of a to from a to x of f of t dt, where x is between a and b, like that. Yeah, so if f is continuous on this, then the integral is continuous. This g of x is continuous on closed interval a and b, and differentiable on a and b, and g prime of x equals to f of x. So the derivative of this function would be f, like that. And then part 2 of the fundamental theorem of calculus is if f is continuous on a and b, then the integral from a to b of f of x dx equals to capital F of b minus capital F of a, where capital F is any antiderivative of f that is a function such that capital F prime equals to f. So yes, in other words, this g of x is an antiderivative of f, because you take the derivative, you get f, and here you can just subtract this, so you can evaluate this integral to get an exact value by getting any antiderivative of f, and then plug in b minus capital F of a, and solve. So that's what we have is, so let's just deal with our equation here after that, a quick recap. So we have this integral right here, integral from a to x of x minus t f double prime of t dt. So let's just go over here. Yeah, so that's what we have is, let's just write what we have first. We have integral from a to x of x minus t. This is be x minus t, and this is power of 1. So just leave it like that. And then f double prime of t dt. Let's just double check again. Scroll up here. And that is exactly what we have. Integral from a to x of x minus t times f double prime of t dt. Scroll back down. So now what we have here is, well, what I'm going to do now is I'm going to let u, so we're going to solve it by parts. I'm going to let u equals to x minus t. That's this right here. So move it there. So that equals to u. So I'm going to let u equals to x minus t. And I'm going to let dv equals to the second part, f double prime of t dt. And this is going to be, well, this whole thing like that is going to be our dv. And the reason I'm doing this is because when you take the derivative of du, because remember by parts, we're going from u dv to uv and then minus v du. So we want to simplify v and du, especially du. And notice here what we have, du is going to be equal to, this is equals to, well, it's going to be negative, this is going to be equals to negative, well, dt, because you take the derivative. And this formation, or this notation, you could just view this as like that, i.e., I'll just put a bracket like this, i.e., take the derivative, du over dt, this just equals to, well, negative 1. So it's not in terms of x, so that's just a constant that goes to 0. And this is going to be negative equals to negative 1, and then move the dt on this side, and we get this or negative dt like that. And also here we have, now we want to get the integral of it, and we want any antiderivative or any integral of this, so this is going to be v is going to equal to, well, f prime of t, like that. In other words, I'll just put a bracket like this, i.e. dv, let's put a bracket like this, dv, integral of dv equals to the integral of f double prime of t dt, and this just equals to antiderivative of f double prime is going to be f prime of t, and then plus a constant c, and here we could choose anything, so we'll just pick choose c equals 0, like that. Yeah, so that's what we have is by applying by parts, because remember it's going to be it's u dv and then uv minus v du, the integral of the first and last part are integrals. So let's just write this down what we have. So we have this full integral. This is going to be integral from a to x of x minus t, and then this is going to be f double prime of t dt, where this is our u, this is our dv, this is going to equal to now u x minus t, and also this is a number, we're taking definite integrals from a to x now. Yeah, so it's from a to x, so we're going to do a big block like this, x minus t, like that, where this is our u. And then our v is equal to this part right here is our v, is just f prime of t, so this can be f prime of t. And this is, we're evaluating it from t equals to a up to t equals to x, and this is where this is going to be our v. And we're going to now subtract this by, now the integral from a to x, so instead of u dv, it's going to be v, so v f prime of t, like that. And then we have to have du, which is right here, negative dt. So if it's negative dt, we just put a plus like that. This is going to be our v, like that. And this is going to be our du, where du right here just equals to this negative dt. Actually, no, I got that upside down. This is our this is our dt, where this equals to negative du, like that. Yeah, we'll put negative du, and we get to, instead of negative, we make that a positive, like that. And now we can actually evaluate this. So this equals 2, so let's write this as this equals 2, and then plug in at x equals 2, this is going to be x minus x. That just goes to 0. So this first one's going to be 0, and then we plug in the next one's a inside the t. So we're just going to have minus x minus a, like that, and then f prime of a. This is the first one, and we plug in x in there, so x minus a is going to be 0. And then the next one here is going to be plus. Now here we're going to be evaluating this. The antiderivative of f prime of t is just going to be f of t. Integral now from a to x, like that. Now this equals 2. And also I'm going to move this actually in front. So I'm going to move this to evaluate that one first. So let's put an arrow like that. So evaluate this one first, and this is going to be, well, f of x. F of x minus f of a, and then add this part after. Minus x minus a, or actually instead of x minus a, let's put this in front. So f prime of a times by x minus a, like that. Yeah, so this is the integral of the theorem, but notice what we have here. Yeah, this right here, f of x minus f of a minus f prime of a times x minus a. This just equals to, scroll up what we had for, so this is what we just evaluated by parts. And then scroll up here. This is actually R1 right here. So for n equals 1, we have R1 of x. R1 of x. R1 of x is equal to f of x minus t1 of x. And we got this over here. So this is equal to f of x minus f of a minus f prime of a times x minus a. So let's box this out. This is exactly what we just solved. So in other words, this equals to R1. So R1 is true. So we have for n equals 1 is true, because this equals to R1. So if we scroll up here from our theorem, and also for induction, so we've proved that R1 is equal to this, which is equal to this right here. So in other words, we've solved for the first case. So S1 is true in our case, n equals 1, so R1 of x is equal to the theorem. Alright, so now that we've shown that the theorem is proved for n equals 1, so this is R1 like that. Now, so we suppose that theorem 1 is true for n equals to k, and then we're going to use the induction and try to prove it for n equals k plus 1. So again, going back here, so we have proved that S1 is true. Next statement is we're going to assume Sk is true, which is in our case n equals k, and then go with, then try to prove S sub k plus 1 is true. So prove this is true. Assuming this, and then once we've done that, we've proved it for all of them, because we can go from 1 plus 2 plus 3 plus 4, etc. So here's our Rn. We're going to place this with Rk, like that. Let's just scroll down here. So now we suppose that theorem 1 is true for n equals k, so we're going to have R sub n of x, like that. This equals to 1 over, actually this is Rk, so we're going to be n equals to k. 1 over k factorial, integral from a to x of x minus t, power of k times it by f of k plus 1. This can be a t and then dt, like that. And again, we want to show that it's true for n equals k plus 2. So this is what we assume is true. So we assume Rk of x is true. So now we just got to prove that n equals k plus 1 is true. So what we're going to do is just write this down for completeness. So Rk plus 1 of x is equals to 1 over k plus 1, like that, factorial, integral from a to x of x minus t. This can be k plus 1. And move this around, minus t, like that. This is going to be now f of k plus 2 t dt. Yeah, all right. So now that we have this, so we got yes, we have assumed that n equals k is true. We're gonna now try to prove that r of this k plus 1 is we have to prove that this is true for this n equals k plus 1. That this statement is true. So what we're gonna do is, again, we could use integration by parts. So this time with, and I'm gonna draw this here. This is gonna be our u, well, this whole thing. So we're gonna pick that as our u, similar to the previous derivation, and this is gonna be our dv. Like that. So again, we're going to use integration by parts where u equals to x minus t power of k plus 1. And let's just take the derivative here. So the du is going to be, just to take the derivative, this k plus 1 goes down. Like that. And then we're going to have x minus t. This is going to be, so let's put an arrow like that. So this is what we get from it. And this is going to be k plus 1. We subtract the powers, this is going to be k like that. And then use chain rule, derivative of negative t. It's going to be negative dt, again, as before. So just move the dt on this side. So now, and then our v. So we're going to have, and I'll put a and v is our, or dv is equal to this part right there. So that's going to be f of k plus 2 t dt, and then any antiderivative is going to be just v, which equals to, this would be the k plus 1 derivative. So one previous t like that, and we just put the constant integration at 0, and we take the integral of that, because we could just choose any antiderivative, we'll choose that, where the constant is equal to 0. So this is what we have, with this and over in the middle, so and that. Alright, so thus integration by parts states, again, let's just quickly see that. Yeah, it's over here, so this is the u dv equals uv minus v du, and then we could evaluate them as a definite integral like that. So let's just write this down. So thus what we have is this r, k plus 1 of x is going to be equal to, and it's going to be equal to, yeah, so this is equal to this part right there. Yeah, so for completeness, I'm just going to write this all out. It's going to be 1 over k plus 1 factorial. Yes, we have to account for this 1 over k plus 1 factorial, and let's write this out. But I'm going to write it out as, this is going to be from a to x of well, better yet, more accurate limits. Can put t equals to a up to t equals to x, and this is going to be our u dv, like that. Dv, u dv, then evaluating this, or using the by parts, this is going to be equals to 1 over k plus 1 factorial times it by, it's going to be uv, and here actually just move it here, it's going to need more space, and just change up this bracket, this is going to be now, and then so we're evaluating it, so this is going to be uv, evaluating it from t equals to a to t equals to x. And then subtract this by, and we're going to subtract this by the integral from a to x of, this is where t equals to a to t equals x. T equals to x, like that. Now we're going to have a v du, again, because there's a du there, so just to not get confused, that's why I'm putting t equals x as opposed to u equals x. So that's what we have. So now let's just plug in all of the variables that we've included here, so all of the values. So this is going to be equal to, it's going to be a pretty big one, so I'm just going to put a 1 over k plus 1 factorial times it by over here, u is going to be, the u is just this right here, so x minus t to the power of k plus 1. So x minus t to the power of k plus 1. And then times it by v, which is going to be right here, the k plus 1 derivative of t, like that. So it's going to be f of k plus 1, like that, t. We're evaluating it out like this. This is going to be again from t equals to a up to t equals to x. And now we're going to subtract by the, this is going to be again, we'll have to multiply this factorial out, 1 over k plus 1 factorial. Integral from a to x, and then now there's going to be the u, or I mean the v. V is the k plus 1 derivative, so it's going to be like that, k plus 1 derivative dt, And then the next one, du, is going to be this negative sign there. So be negative is going to be positive. Negative k plus 1. And the k plus 1, it's not in terms of t, so we just move that over here. Just to save some space, this be k plus 1, like that. And then lastly, we're going to have this x minus t to the power of k, and then dt. It's going to be a x minus t to the power of k dt. Alright, now that we have this, let's start evaluating and also simplifying. Notice here, this is k plus 1 factorial. This just equals to k plus 1 times it by k factorial. So that we have that, this cancels out with this top part. So now we're just going to have a k factorial there. And also now if we evaluate this, when we plug in x inside this right here, we're going to have an x minus x. That's going to be a 0. So we're going to have a, and here we're going to multiply this all inside. So we're going to have a 0, because the first one's going to all vanish. Then when we plug in the t equals to a, we're going to have, and I move this inside, it's going to be a minus 1 over k plus 1. Again, we're minusing because we're evaluating this, we're evaluating these terms like that from t equals a to t equals x as per the fundamental theorem of calculus part 2. So this is going to be like that, and now it's going to be a multiplied this by this. Yeah, this one when t equals to a, so we're going to have a x minus a to the power of k plus 1. This is going to be f of k plus 1 of a, like that. And then this is going to be plus, and here's going to be a, because this cancels there, 1 over k factorial times it by the integral from a to x of, and now let's just write this out in the form we're used to. Move this in front, k minus t to the power of k, and then this is going to be f of k plus 1. This is of t, and then dt, like that. Alright, now that we have this, and notice we have this part right here. This is the 1 over k factorial. This is x minus t to the power of k times f to the power of k plus 1 t dt. That's exactly this part right here. That's just rk. This is 1 over k factorial, integral from a to x, and there's x minus t to the power of k. This is k plus 1. This is k plus 1, there's k, 1 over k. So in other words, this right here is, this whole thing is equal to rk, like that, of x. Alright, now that we have that, and this part here, if we just simplify this all out, we're going to have this out, just write it all out. It's going to be a negative 1 over k plus 1, so 1 over k plus 1 factorial, times it by, here we're going to put this this derivative part first. I'm actually going to write it on top, so I'm going to write this on top. It's going to be f of k plus 1, like that, of a, just to make it resemble more like, well, in fact, the Taylor polynomial. This is going to be, or this is the k plus 1 term of a Taylor series, like that. And then lastly, just add this this right there. It's going to be x minus a times by k plus 1, like that. And then plus this rk of x. And again, recall, this is just a Taylor polynomial. This is going to be the t of k plus... actually, no, we'll get to that after. This is the last term of the k plus 1 Taylor series. But before I get to that, recall this part right here. This equals to f of x. This is just a remainder. It's going to be f of x minus the Taylor series at the kth Taylor series right there, or Taylor polynomial. It's going to be like that. And again, let's just scroll up for a refresher. Yes, scroll up here. So remember, r1 of x equals to f of x minus t1 of x, like that. So yeah, so we have that scenario. So here, recall this. So we can write, so f of x equals to tn, the Taylor series, or the nth degree Taylor polynomial of f at a. And this is going to be, this is the nth one, and this is going to be plus r of n, that's the remainder of x, and then we just move this over to the other side, so we're going to have rn of x equals to f of x minus tn of x. But in our case, well, for the first one, n equals 1, we're going to have r1 of x equals to f of x minus t1 of x. So now for rk of x, this just equals to f of x minus tk of x. So let's just write this in front. So, and let's move this, let's move it in front. So this whole thing equals to, and we'll put this in front, f of x minus tk of x. And then right here is going to be minus f, so yeah, move this over to this side, f of, this is the k plus 1 derivative of a, like that, at a. This is going to be k plus 1 factorial, and now we have an x minus a k plus 1. In other words, this is just the term right after this, the kth term. This is just a Taylor series terms. So in other words, this combines into, we're going to have here, this equals to, move it all the way across, this whole thing equals to fx minus tk plus 1 of x. Okay, so that's what this equals to, and in fact, this just equals to, this just equals to over here, because remember this is rk of x equals fx minus tk of x, so now this fx minus tk plus 1 of x, this just equals to rk plus 1 of x, like that. So in other words, this whole thing equals to rk plus 1 of x, where initially we try to prove it, and there it is. This is what we started off with, and we end up with the exact same thing. So thus we've proved that this is actually true. So let's put this here. This whole thing was this rk plus 1 of x. So we start off, we assumed it, and then we evaluated it and proved that in fact it is equal to this. So yes, this rk plus 1, r of k plus 1 of x equals to fx minus tk plus 1 of x, and in fact is equal to itself. So rk plus 1 of, rk plus 1 of x, like that. So this is double check mark for that. Yeah, so therefore theorem 1 is true for n equals k plus 1 when it is true for n equals to k. Thus by mathematical induction it is true for all n, because remember n equals 1 is also true. So to illustrate now theorem 1, we use it to solve example 4 from my earlier video and referenced below. Just for a refresher here, just a link to the SteamIt one, and again there's a screenshot from my calculus book because it's more compact. So example 4 states find the Maclaurin series for sine of x and prove that it represents sine of x for all x. And solution, we arrange it as such this way. Get the derivatives, write the Maclaurin series, and then get it like this. And then I showed that since n plus 1 derivative of x is equal to plus or minus sine of x or plus or minus cosine of x, we know that this is less than, the derivative is always going to be less than or equal to 1 for all x. And then using Taylor's inequality, we get this form right here. And then by equation 1, from my earlier video, the right side is inequality approaches 0, so we could use a squeeze theorem. And yes, it follows that this remainder approaches 0 by squeeze theorem, and then it follows that when the absolute value of the remainder approaches 0, also this is also approaching 0. So then because the remainder is approaching 0, sine of x is equal to 0. Again, it says as n approaches infinity. And then it's equal to the sum of its Maclaurin series. So then, and also a state for reference, sine of x equals to this right there for all of x. And again, equation 1 noted above, which I'll be referencing. Yes, so also note equation 1. It's noted above in here. So by equation 1. And I'll be referencing this later in this video, so just put this right here. So limit as n approaches infinity of x to the power of n divided by n factorial equals 0 for every real number x. And also note the squeeze theorem, which was used in above example from my earlier video and will be used in example 1 of this video. So remember the squeeze theorem. So if we have f of x is less than or equal to g of x, which is less than or equal to h of x when x is near a, except possibly at a, and the limit as x approaches a of f of x equals to the limit as x approaches a of h of x. So if the limit of f and h are approaching the same limit L, then the limit as x approaches a of g of x is also equal to L. If this, because remember the g of x is always in between these two. So the outer ones have the same limits, the inner one as well. So in other words, it's just getting squeezed inside there. And then for series, it's similar for series. So if we have a sequence like this, or sequences like, for sequences in series. So if we have an is less than or equal to bn, less than or equal to cn, for n equals to, n is greater than or equal to n naught, or the starting point, then, or n naught or a specific value n like this, then the limit as n approaches infinity of an equals to the limit as n approaches infinity of cn equals to L, then one in between is also equal to L, the limit. So in other words, it's exactly the same thing here, but now here we're dealing with sequences. Right there, they sum up. The terms are approaching. Yeah, they're approaching the same as the one above it, because this bn is always between an and cn. So then, if they have a limit, the one in between also has the same limit. So the sequence bn is squeezed between the sequences an and b and an and cn. So, anyways, just want to refresh on that. So now we can go forward and look at example 1, and say find the Maclaurin series for sine of x and prove that it represents sine of x for all x. Again, it's the exact same thing here, but instead of using Taylor's inequality, Instead of using Taylor's inequality over here, we're going to use the theorem one that we just went over. And first of all, we're going to get the derivatives and do the exact same thing as we did over here. Just going to do it again just for completeness. And then we'll start to solve for the remainder to show that it approaches 0. So, solution, we arrange our computation in two columns as follows. So we have sine of x. We're going to write this as f of x like that equals to sine of x. Remember, the derivative of sine of x, f prime of x, is going to be, this is going to be negative, I mean not negative, it's going to be this cosine of x. Then the derivative of double prime of x, of cosine of x, is going to be equal to negative sine of x. Negative sine of x, like that. And also just keep writing it over here. So f of 0, when we plug in, remember we're dealing with Maclaurin series, this is when a equals 0 for the Taylor. So plug in 0 inside, so sine of 0 is, remember, is just going to equal to 0. And then cosine, when you plug in 0, is going to be 1, so f prime of 0 equals to 1. And then f double prime of 0 is equal to negative 0, which is 0. And then keep going further, so this is going to be f triple prime of x. This equals to negative cosine of x, which equals to f triple prime of 0. This equals to negative 1. And then let's go one more. This is going to be the fourth one. Let's put a 4 like that of x. This equals to, this is going to be negative. There's already a negative there, so negative sign, so negative becomes positive. It's going to be sine of x. And now we've started repeating. This is the fourth one of 0. This equals to 0 like that. So here's a repetition right here. So from here to here, it repeats. Alright, so now since the derivatives right here repeats in a cycle of 4, because remember the derivative goes from sine of x all the way to cos, negative sine, negative cos, and then positive sine. So we're all the way back to where it started. And we have this 0, 1, 0, 1, etc. So since the derivatives is repeated in a cycle of 4, we can write the Maclaurin series as follows. And if you have the Maclaurin series imprinted into your brain, as I have from doing so much of this Taylor series, I already know just already memorized it. So n equals 0 to infinity, and remember Taylor series is just going to be Taylor series with a equals 0, so it's going to be the derivative on the top at a, which is 0, divided by the factorial, which is n factorial, and then this is going to be now x minus a, but a is 0, so x to the power of n. And now this equals 2, so the first one at n equals 0 is just going to be, well, the 0, 1 is just going to be the same as the first, just the function f of 0, well, I mean the function f of x, but this is at 0, and x to the power of 0 and 0 factorial are both defined as equaling to 1. So that's going to be the first term. The next term is going to be f prime of 0 divided by 1 factorial. It's going to be x to the power of 1. And then the next one is going to be f double prime of 0 over 2 factorial. It's going to be x to the 2, and the next one's going to be plus f triple prime of 0 over 3 factorial x to the 3, and then plus dot dot dot. Alright, now that we have this, let's plug in our values for the derivative. So at 0, so f of 0 is 0, so plug this in. Let's move some space over here. It's going to be 0 plus, or actually just write it right next to it. So it's going to be 0 plus, and then the first one's going to be 1 over 1 factorial times x is going to be x. And the next one, f double prime, is going to be 0, so plus 0. And then, then we're going to have the next one's going to be a negative like that. So that's the third derivative. F triple prime is going to be a negative. So negative 1. This is going to be x cubed over 3 factorial. And then, as you can see, it keeps going on and on. So the next one's going to be a minus 0, which is still going to be 0. Then I'm going to switch to plus, and then plus x5 over 3 factorial. And then it's going to be a plus 0 plus, etc. I'm just going to go dot dot dot. And then minus these, remove the zeros, would end up having as x minus x over 3 factorial plus x to the 5 over 5 factorial. Actually, yeah, this is not a 3, this is a 5. And then 5 factorial, and then the next one's going to be, well, minus x to the 7, as you see the pattern. And then next one's going to be plus minus dot dot dot. And this whole thing's going to equal 2. Write this in series notation from n equals 0 to infinity. And then it's going to be alternating signs, so we're going to have a negative 1 to the power of n. So when n equals 0 is positive, n equals 1 is negative. So positive, negative, etc. And then we're going to have a, here is going to be x to the power of, so when n equals 0, we need power of 1. Then when x equals to 1, we need 3. So in other words, we're going to have a 2n, because it's moving by 2's. So 2 times 1 would be, 2 times 1 is 2 plus 1. Just like that. And then when this is 2, so when n equals to 2, we're going to have a 2 times 2 is 4 plus 1. So we'll add an extra 1. This is all divided by 2n plus 1 factorial. Like this. And now just do a double check with our previous, so let's just double check with our previous example for my earlier video. So here we have the summation from n equals 0 to infinity. You have negative 1 to the power of n times x to the 2n plus 1 divided by 2n plus 1 factorial. That's for all x values, as is this one here. So I'm just going to box this out like that. Alright, so now that we have this, now with a equals 0 for the Maclaurin series, in Theorem 1 the remainder is, and we're going to have Rn of x is equal to, this is going to equal to, now remember this is going to be 1 over n factorial, integral from a equals 0 to x. Remember this is going to be x minus t to the power of n. This is going to be now f of n plus 1 factorial. I mean, not factorial, f of n plus 1 derivative of t dt, like that. And now that so we have this remainder term, remainder formula. So now since the derivative n plus 1 of t is always going to be just plus or minus sine of t, or plus or minus cosine of t, because remember our function f is f of x equals to sine of x. So it's always going to be this. So then we know that the absolute value of this derivative is going to be less than or equal to 1 for all t. In other words, recall. So let's put this here. So recall if we have this xy axis, like this is x, this is y, and if we have sine like that, sine goes up and down like that, this is our sine of x. Sine of x, we'll actually put it like this, this is our sine of x. The value here is always going to be between 1 and negative 1, so it's never going to go beyond that. And then draw in red, we're going to have this cosine like that. And then this just goes like that. So you draw that again. So it's going to go from the bottom of this cosine is going to be at the peak of the sine. Remember, just inverse of each other. And then it goes to peak. Then it peaks at the bottom here. While this is at the minimum, and then goes to peak over there. So I'm just going to put dots here. So it's going to go across there. So it should be across there, like that, and it goes like that. And then reverse side, it's going to go to 0 there. Go to its peak over here. Again, it's not the scale, it's the drawing. And then it keeps going on and on like that, and so on. So this is going to be our cosine, cosine x, just for. Alright, so now we can go further. Well, actually, before going further, I will prove the following integral property, which I should have proved in an earlier video years ago. I'm not sure why I didn't, but anyways, let's just jump right in. So here's the absolute value integral property. So if f is continuous on a and b, that is a is less than or equal to b, then the absolute value of the integral from a to b of f of x dx is going to be less than or equal to the integral from a to b of the absolute value of f of x dx, like that. Alright, so now to see the proof for this one, we know that, well, we know over here f of x is going to be less than or equal to, and the proof for this, it's pretty straightforward, because if you just look at this right here, notice here, if you have the integral right here, where the absolute value sign is on the outside, you might have some negative stuff in that cancellation, and they cancel out. So it could be smaller than this one here, where you're always taking the absolute value and finding that area underneath that curve. So this one is enforcing that it's always the highest value for this f of x that you're integrating about. So so obviously it should be greater. But anyways, let's go through the proof. So we know that f of x is going to be less than or equal to the absolute value of itself, and as well as greater than or equal to the negative of the absolute value of itself, like that. So if we have this, that's what we have is, well, thus, if we take the integral of every single one of these, we'll see that the inequality fits for all of them, because this one, negative absolute value of fx is always taking the smallest value of this fx when you're taking that area under the curve or the integral. So it's always going to be like this. So this is going to be we're going to write this as the integral from a to b of the absolute value of the overall of it, and then put a negative sign here, fx, like this, dx. Actually, not the absolute value over there, put the absolute value right here. So this is the function fx, absolute value of fx like that, put the negative out there. So this is going to be less than or equal to the integral from a to b of fx dx, because this one can be positive, negative, have some cancellation, and so on. But then this one here, we're always taking the smallest value of it by putting a negative. And then this is going to be less than or equal to the positive side. So we take the absolute value of it always. Integral from a to b of the absolute value of fx dx like that. Yeah, so now that we have this right here, but notice this part right here, we can write this as, let's say this is g of x, say equals, let's say that equals to g of x, or just let it equal to g of x. Then applying this exact same scenario, so we can apply the same thing, and we're going to get, well, g of x is less than or equal to absolute value of g of x, like that, and which is greater than or equal to negative absolute value of g of x, like that. So this is the highest value it can be, is right here, but we could just plug this inside there. So this whole thing is going to be less than or equal to absolute value of g of x, which this is going to be less than or equal to this side. This is the highest value that this can be, or this g of x. So this is going to be less than or equal to a b, like this, absolute value of fx dx, like that. So in other words, this right here, put this all out, this is just going to be the integral from a to b of fx dx, all absolute value. It's going to be less than or equal to, and this can be integral from a to b of absolute value of fx dx, like that. Alright, here, so I've boxed this in. So now that we have this proof, let's put a check mark. So thus in our case, and for x is greater than 0, we have, and what we could do is, well, we could take this this remainder theorem that we have, that we have derived, and then similar to a previous video and also an example 4 of the last video, I would look at the absolute value. So let's just take the absolute value of this entire integral. So what we're going to have is, thus we have the absolute value, Rn, of the remainder, is going to be, let's write this better. Alright, so this absolute value is going to be less than or equal to, and let's just take the absolute value of the whole thing. But since this is positive, we can just leave this out. So 1 over n factorial is always going to be positive. Just put this in the integral, and this is for x greater than 0. In other words, we have b is greater than or equal to a, or a is, in this case, we'll have 0. It's going to be x. Like that. So 0 is less than or equal to b. So in this case, here is going to be a 0, because we're doing the Maclaurin series up to x, like that. And remember, this is going to be x minus t to the power of n. So let's go over here again. Let's look at this x minus t to the power of n. This is going to be n plus 1 derivative over there. So now we're going to have f n plus 1 derivative of t dt, like that. So using this above property right there, the integral property, so this is going to be less than or equal to, where the integral is inside the function there. This is going to be less than or equal to 1 over, this is going to be 1 over n factorial, and now we could put the integral inside. But this x minus t, because we're plugging in this x, which is always going to be greater than 0, and we're going to x minus that, so the highest it can get is actually, well, actually the lowest it can get is actually just 0, so this is always going to be positive, so we can just remove that from the absolute value, like that. This is going to be right here greater than or equal to 0, and then we're going to have this absolute value right there, so absolute value of the derivative n plus 1 derivative of t, like that, dt, like that. So we put that absolute value inside. Remember this one right here, we already know that this is going to be less than or equal to 1. Yeah, the absolute value is less than or equal to 1, and this is because we know that the absolute value of this, because the derivative is just going to be plus or minus sine t, or plus or minus cosine t, as I showed over there. So that's always going to be less than or equal to 1. And this one's always greater than or equal to 0, so we can remove this entire absolute value sign out of there. So this can be less than or equal to 1 over, and this is going to be 1 over n factorial, put that like that. 1 over n factorial, and then it's going to be integral from 0 to x of, and now this is going to be just x minus t, power of n dt, like that. And now we could just evaluate this integral. This equals to 1 over n factorial. And then this is going to be, integral of this is going to be x minus t. And this can be n plus 1 over n plus t. And also there's a chain rule there, so we put a negative. Because when you take the derivative of this, n plus 1 goes down. This cancels, minus 1. And then we get this chain rule to account for this negative. And they're going to evaluate that from, like this, put this better. Evaluate from t equals to 0 up to t equals to x. And now this equals to 1 over n factorial. Plug in x, this goes to 0. So we're just going to have a 0 like that. Let's put this, actually just put it like that. So this is going to be negative 0. And then minus and negative is going to be positive. And then just plug in 0 inside. We're going to have an x minus 0. That's just going to be, well, x to the power of n plus 1 over n plus 1. Like that. Yeah, so we have this. And now what does this equal to? Well, this just equals to over here. We get simplified further. This 1 over n factorial times, remove this 0 there. It's going to be x to the n plus 1 over n plus 1. In other words, this is just n plus 1 factorial. Like that. So this equals to 1 over, or better, just put the x over there. So x over n plus 1 over n plus 1 factorial, like that. So yes, this is equal to, or this is equal to this side here. So basically the remainder, absolute value of the remainder is less than or equal to this over here. Alright, so now that we have this scenario, this is for x is greater than 0, but now let's look at when x is less than 0. So for x is less than 0, we can write, over here, Rn, so Rn, the remainder, is equal to the, again, integral from 0 to x of, this is going to be x minus t to the power of n, and then this is f n plus 1 t dt, and now this equals to, just remember there are integral properties. This could be, when you move this around, you can flip it and this would be negative from x to 0, so that this, so we can apply the integral property for the absolute value sign soon. So this can be negative x minus t power of n. This is fn plus 1 t dt, like that. Like this. And yeah, actually I forgot to include the 1 over n factorial, so move this over. It's going to be 1 over n factorial, move this over. This will be 1 over n factorial. Yes, so what we have is we could just take the, let's move this over here. So now we can just take the absolute value sign again, but now we have this negative and that just goes away. So it's going to be absolute value of the remainder, Rn of x, is going to equal to, and having this negative sign, well, that just vanishes because it's taking the absolute value sign, just make it positive, and we're going to put this 1 over n factorial, that's always going to be positive, and just put this now here from x 0. This is going to be x minus t to the power of n, it's going to be f to the n plus 1. T dt, like that, and this is all around it. So now this around is going to be equal to, or less than or equal to, 1 over n factorial. And yeah, now inside of this, well, we're going to just put the absolute values inside, so this is going to be from x to 0. Now this one here, this is the, we're taking the absolute value of this is x minus t, where, you know, where this x is less than 0 already. So we're also going to be subtracting. It's going to be negative always, so we just take the absolute value of it. So notice the absolute value sign. Just put an arrow like that. Notice the absolute value signs there. From this bracket now it's absolute value sign because we're taking absolute value sign inside. It's x minus t, like that, to the n. This is going to be absolute value of this, n plus 1 t dt. Yeah, like that. And this is going to be dt. And now this part right here, we know that this is going to be less than or equal to 1. Let's put this a bit better. Like that. This is going to be less than or equal to 1. And this one right here, we could rewrite this, or this can be now, it's going to be less than or equal to, and make that equal to 1, less than or equal to 1 over n factorial. It's going to be from x to 0. And now here what we can do is just move this around. Because, well, inside here, this is x is always going to be less than 0, and then we're subtracting 1, so this one's always going to be less than or equal to 0. So it's always going to be negative or 0. And now here we made it always positive, and now we could just, if you want to make it all positive without this absolute value sign, we could just flip this around so we could have a t minus x. So you just put a negative sign instead of this, like that. So now what we have is t minus x, where x is always negative. This is going to be, well, this is going to be greater than or equal to 0. So always positive, like that. And then this one here is gone because it's less than or equal to 1. So we have this. And now we can evaluate this integral. This equals to 1 over n factorial. This is going to be, and now we get a t minus x. Integral of this is going to be n plus 1, and then divide this by n plus 1. And then the chain rule, there's nothing in front of the t because we already moved it. So just leave it like that. This is going to be from x to 0. So now, yeah, this is going to equal to 1 over n factorial. And I'll plug in 0 inside this right there. So we are going to have a 0 is going to go in this t. So we're going to have a negative x to the power of n plus 1 over n plus 1, and now minus x. Oh yeah, minus when you plug in x inside, that just vanishes. So we're just going to get a minus 0, like that. So in other words, this just equals to negative x to the power of n plus 1. This is going to be divided by n factorial n plus 1, and we already know what that is. That is just going to be negative x to the power of n plus 1 over n plus 1 factorial. Like that. And now there is what we have. And this is exactly the same thing as above over here, but this is instead of negative x is x, and but the values are exact same when you take the absolute value. And thus, in any case, we have, because remember, we start off from the absolute value of the remainder is less than or equal to this value there, and then for the one above, it's less than or equal to this right there. So yes, that's where we start off. So in any case, we have absolute value of the remainder Rn of x is less than or equal to, and this one's going to be, yeah, just take the absolute value of this x like that, power of n plus 1, and this is divided by n plus 1 factorial. Alright, so we have this, and now the right side of this inequality approaches 0 as n approaches infinity, and this is, let's put a space, and this is as per equation 1 from my earlier video referenced earlier above. So let's just scroll all the way up to it and see where we have that. And that is right over here. So this limit as n approaches infinity of x power of n divided by n factorial. And yeah, this goes to 0. And in our case, just n plus 1. And this one's n plus 1 factorial, but it's the same thing. So that approaches 0 again from my earlier video. So check that out if you so wish. So thus, what we have is thus the absolute value of the remainder Rn of x. Yeah, the remainder approaches 0. The absolute value of the remainder approaches 0 as n approaches infinity. Just fix that up quickly. By the squeeze theorem. And again, recall this is basically if we have 0 is less than the limit. Yeah, limit as n approaches infinity of the absolute value of the remainder Rn of x, like that, which is less than or equal to the limit, as again by per the squeeze theorem. So if we have this inequality, take the limit, and then this one's a positive, so it's greater than or equal to 0. So we have, to the left of it is this, the limit of n approaches infinity of 0 is just 0. This is going to be n approaches infinity, and this is going to be absolute value of x, power of n plus 1, like that, all over n plus 1 factorial. And where we know that this is from equation 1, this approaches 0 like that. So in other words, this right here gets squeezed. So this is this gets quote squeezed like that. And so yeah, squeeze. Thus, what we have is, so yeah, thus this also approaches 0. So if it's less than or equal to if it's less than or equal to 0 and greater than or equal to 0 for and then the limits of those are also approaching 0, then yeah, I mean if the limit is going to be greater than or equal to 0 while less than or equal to 0, it's just 0. So it's approaching 0 because both sides are approaching 0, and it gets squeezed inside. So then the absolute value like this, Rn of x, is equal to 0. And yeah, thus it follows now that because the absolute value is approaching 0, that they're just without the absolute value is still approaching 0. So then that the remainder Rn of x is approaching 0 as n approaches infinity. So sine of x is equal to the sum of its Maclaurin series because the remainder is approaching 0. Alright, now that we've covered all this, now let's look at the next form of the remainder term, and that's Lagrange's form of the remainder term. And yeah, let's just go dive right in. So for some purposes, the integral formula in Theorem 1 is awkward to work with, so we are going to establish another formula for the remainder term. To that end, we need to prove the following generalization of the mean value theorem for integrals. But first, a quick recap on the mean value theorem. This was the original one for derivatives, and then also for integrals from my earlier videos. So here's the links below. And here's do a quick recap. So recall the mean value theorem. This is for derivatives. Let f be a function that satisfies the following hypotheses. F is continuous on the closed interval from a to b, and f is differentiable on the open interval a to b. So these are not including a and b, or not having to include a and b. Then there is a number c in a and b such that the f prime of c is equal to f of b minus f of a divided by b minus a. In other words, is the average or the mean. So there's a derivative at a point c that is the average. Yeah, that is the average value of the function. Or equivalently, right here, f of b minus f of a. So just move this over to this side. Equals to f prime of c times b minus a. So before proving this theorem, just reading from my calculus book, we could see that that it is reasonable by interpreting it geometrically. Figures 3 and 4 show the points capital A and B like this. This is A, this is B. Yeah, it shows it on the graphs of two different differentiable functions. So here's A and B over there. And then the slope of the secant line A to B, this slope right here is just going to be f of b, which is at this point here, minus f of a divided by b minus a. And same for this one here. And this line, notice that it's a straight line, like that. And there's going to be a point across like this, or in this case, we'll have c1 and c2. 2 points that have the exact same derivative, same slope. So this is same. This is same as this one here, like that. So yes, that is the mean value theorem, and which is expression as on the right side of equation 1 over here. So this is just the average value or the slope of the secant line, yeah, between the endpoints. And since f prime c is the slope of the tangent line at the point c and f of c, the mean value theorem in the form given by equation 1 says that there is at least one point p. Yes, a point at least one. You can have multiple, so there's P1, P2, but this one at least one. P, which has the x c, the y is f of c, on the graph where the slope of the tangent line is the same as the slope of the secant line AB. In other words, there is a point P where the tangent line is parallel to the secant line. Secant is from A and B, and this is tangent to this point. And now going over the mean value theorem for integrals. Recall this is if f is continuous on the closed interval a to b, then there exists a number c in this interval a to b such that f of c equals to f of average, or equals to the average value, which equals to 1 over b minus a times the integral from a to b of fx dx. Yeah, or you could write it like this: integral from a to b of fx dx. So here, just move this b minus a to the other side. Equals to f of c times b minus a, where this is the average value, and the mean value theorem for integrals is the consequence of the mean value theorem for derivatives and the fundamental theorem of calculus. The proof is outlined in exercise 23. That's in this link there. The geometric interpretation of the mean value theorem for integrals is that for positive functions f, there is a number c such that the rectangle with base capital A to b and height f of c. Yeah, so this rectangle right here, this is a height. So this rectangle in pink over there, and this is from A to B there, and then the height is f of c. That's the average, and height has the same area as the region under the graph of f from A to B. So this interval, integral right here, the area for this positive function, is going to be equal to the average value, or this rectangle, like that. So yes, you could squeeze that into a rectangle, and that is where this f of c is. And has same area as the region under the graph of f from A to B. And see figure 2 and the more picturesque interpretation in the margin note. So here you can always chop off the top of a two-dimensional mountain at a certain height and use it to fill in the valley so the mountaintop becomes completely flat. So you can cut this off, this area, throw that in here, and you get a flat plane. Alright, so now that I recapped on the mean value theorem for derivatives and integrals, let's look at Theorem 2, weighted mean value theorem for integrals. So if f and g are continuous on the closed interval a and b, and g does not change sign in a and b, then there exists a number c in a and b such that the integral from a to b of, this is fx, g of x. And again, this is all because before I get to the Lagrange form of the remainder term, we're going to go over this weighted mean value theorem for integrals. So I'm just going to prove this first. So this equals 2, so fx gx times dx, fx times g of x dx of integral from a to b is equal to f of c, so a number c inside it from a to b, and g does not change sign, so it's either all negative or all positive. This is from a to b of g of x dx, like that. And yeah, so now let's look at the proof. So because first of all, because g doesn't change sign, either we have g of x is always going to be greater than or equal to 0, or yeah, so this is, or g of x is less than or equal to 0, and this is for the interval from a to b. So for integral from a to b where x is greater than or equal to a and less than or equal to b, like that. Alright, so now that we have this out of the way, so for the sake of definiteness, let's assume that g of x is greater than or equal to 0. So let's consider this case. So by the extreme value theorem, also referenced below from my earlier video, f has an absolute minimum lowercase m and an absolute maximum capital case or uppercase capital M, yeah, like that. And here's a link from my earlier video on the extreme value theorem. So we have seen that some functions have extreme values, whereas others do not. The following theorem gives conditions under which a function is guaranteed to possess extreme values. Extreme value theorem: if f is continuous on a closed interval from a to b, then f attains an absolute maximum value f of c and an absolute minimum value f of d at some numbers c and d in interval a and b. Now, in our case, f is continuous from a to b, and so yeah, so f is over here continuous from a to b, so it has absolute minimum and absolute maximum values. So here, extreme value theorem is illustrated in Figure 5. Note that an extreme value can be taken one or more, taken on more than once, as over here. I mean, extreme value. So in this case, c is over here is the highest, and d is the lowest in between these two, and here's the c is the absolute max. And this is the d is equal to b, in this case, absolute minimum. And here we have two absolute max, c1 and c2, and it has one absolute minimum over d over there. So although the extreme value theorem is intuitively very plausible, it is difficult to prove, and so we omit the proof. And yeah, I'm not sure if I proved it in this earlier video. I don't think I proved it, but I should have. But anyways, going further, so might prove it in a later video. So figures 6 and 7 show that a function need not possess extreme values if either hypothesis, continuity, or closed intervals is omitted from the extreme value theorem. So here we have over here is discontinuity, so it's not continuous, and this is from so at this point here, it doesn't have an extreme maximum here because this value never actually reaches that exact point. And over here, this is a continuous function. G has no maximum or minimum. Yeah, it's continuous. It keeps going up, and there's no minimum here. This is an open interval. It doesn't have a point there, and this one goes to infinity, so it never actually reaches that value. And here, this function has a minimum value f of 2 equals to 0. That's over this one, but no maximum value. This is open interval. That. So anyways, the function f, whose graph is shown in Figure 6, is defined on the closed interval 0 to 2, but has no maximum value. Notice that the range of f is 0, yeah, so 0 and 3. Yes, from closed interval 0 to open interval 3. The function takes on values arbitrarily close to 3, but never actually attains a value 3. This does not contradict the extreme value theorem because f is not continuous in this case. Nonetheless, a discontinuous function could have maximum and minimum values. See exercise 13b. Anyways, so thus in our case, by the extreme value theorem, we have a continuous function f of x from a to b. So we're going to have to have f of x is going to be greater than or equal to the lowercase m for the smallest value, and it's going to be less than or equal to capital case M for the extreme maximum. And this is for a is less than or equal to x, which is less than or equal to b. And now, since g of x is greater than or equal to 0, we're going to assume that case. We have, because remember, it doesn't change sign, and we're just going to go for this first scenario. So we have g of x is greater than or equal to 0. So when we multiply that out in this inequality, we're going to have m times g of x is less than or equal to f of x times g of x. We're just multiplying it all by positive number g of x. And this is going to be less than or equal to m times g of x, like that. Yes, now that we have this, and again, this is for a is, let's write it here for completeness, for a is less than or equal to x, for a less than or equal to x, less than or equal to b. Yeah, so we have that, and now what we can do is take the integral on every single term, so that, yeah, integral on the left side is going to be less than the middle one, less than the right one there, as in the integral property that I went over earlier. So this one is going to be, integral is going to be like this. And actually, integral is going to be from a to b in terms of x. So we can just take this m out as just a number, positive, just a constant. So this is from a to b of g of x is going to be less than or equal to, less than or equal to the integral from a to b of f of x gx, like that. And then this is dx. And again, because g of x doesn't change sign, so we didn't change anything there. And now it's going to be less than or equal to integral from a to b. Actually, put the capital M in front. Just a constant. Integral from a to b of g of x, like that, dx. Alright, so now that we have this inequality, so now let's look at the simple case. So if we have the integral from a to b of g of x dx is equal to 0. If it equals to 0, then these inequalities above there, that's going to show is going to be, well, it's going to be m times 0 is less than or equal to integral from a to b of f of x gx times, this dx less than or equal to m times, well, 0. So in other words, this just goes to 0 there. This equals to 0. This equals to 0. So this is going to be in between 0. The only value could be is 0. So that's what we have is integral from a to b of f of x g of x dx is equal to 0, like that. Yeah, and so for this case, theorem 2 is true because both sides of the equation are 0. That is, if we scroll up to the mean value theorem, so it's over here, integral from a to b of fx gx dx, and then we have f of c times integral from a to b of g of x dx. And those are both 0, because this one we know is 0. We just show that as 0, and this g of x is that's assuming a 0. That just goes to 0. So let's write that down. So because it's 0, that is integral from a to b of fx gx dx is equal to 0, which equals to, this is just a constant f of c, integral from a to b g of x dx, like that. So they both equal to 0. Like that, because this one goes to 0. Alright, so this is the case where integral from a to b of g of x dx is equal to 0. But now if we have the scenario, integral from a to b of f of x dx is not equal to 0. Yeah, so if this is not equal to 0, this is g of x, not f of x. So if this is not equal to 0, then it must be positive, because we had it before as g of x is going to be greater than or equal to 0. Yeah, so it must be positive here, because we're taking integral from a to b of a positive function there. Then we can divide the earlier inequality without changing the actual signs, without changing these inequalities. So we can just take this one here and divide this by this integral from a to b of g of x dx, because that is constant. So what we'll have is, as we'll divide by it, and what we're going to get is on the left side, m is going to be, well, dividing by integral from a to b of gx dx. This is supposed to be a dx there. A good spot. Let's see if I made any other mistakes. Nope. Okay. Yeah, so this one we can divide it out. This cancels, this cancels. So we're going to have m is less than or equal to the integral from the middle one. So integral from a to b of f of x gx dx. And make this better. A. Divide this by integral from a to b of g of x dx. This is going to be less than or equal to capital M. Alright, so now that we have this part here, now we're going to recall another value theorem. This time, recall the intermediate value theorem from our earlier video here. So an important property of continuous functions is expressed by the following theorem, whose proof is found in more advanced books on calculus. Interesting. I should get on this. So suppose. So yes, I'm not sure why I didn't prove it before, but I should prove it in a future video. But anyways, so the intermediate value theorem is pretty straightforward, just the proofs are more rigorous beyond this calculus book. So the intermediate value theorem, suppose that f is continuous on the closed interval from a to b, and let capital N be any number between f of a and f of b, where f of a is not equal to f of b, then there exists a number c in the open interval a and b such that f of c is equal to capital N. And again, it's basically saying here the intermediate value theorem states that a continuous function takes on every intermediate value between the functions f of a and f of b. It is illustrated by figure 8. Note that the value n can be taken on once, as in part A, or more than once, as in part B. So here basically saying if you have a continuous function from here to here, and then there's going to be a value in between. That's pretty much it. But in mathematical lingo, the exact proof for this is a bit more rigorous, but it's pretty straightforward when you look at the graph. So here f of a, this is to here, you have multiple values of n like that cutting through. So you have c1, c2, c3, and like that. So basically any, so n just any value in between. And if we think of a continuous function as a function whose graph has no hole or break, then it is easy to believe that the intermediate value theorem is true. In geometric terms, it says that if any horizontal line y equals n is given between y equals f of a and y equals f of b, as in figure 9 here, then the graph of f can't jump over the line. It must intersect y equals n somewhere. It is important that the function in theorem 10 be continuous. The intermediate value theorem is not true in general for discontinuous functions. See exercise 44. One use of the intermediate value theorem is in locating roots of equations, as in the following example in the video, but not in this. So as you can see here, yeah, so basically if you draw a line, it needs to go through. So you're going to cross it there, you can't just jump over it. No jumping. So yes, fascinating stuff. So then by the intermediate value theorem, by the intermediate value theorem, there exists a number c in a and b such that, if we scroll up above here, scroll up above here. So here, this overall function, this integral divided by integral, is greater than or equal to m and less than or equal to capital M. Those are the extreme values. So then there has to be a value that is just equal to this. We just put f of c is equal to this value, and whatever this integral is. So this is going to be a value in between that. So in our case here, this could be considered as lowercase m's, capital case M, and then somewhere in between. It's going to have a value. So then by it, we're going to have a number, there exists a number c such that f of c is equal to, the function in between, so from integral from a to b of f of x gx dx over integral from a to b of g of x dx, like that. And thus we can just take this and move it over to this side, and what we're going to end up having is, and also rewrite this in front, so move that over to the other side. So we're going to have integral from a to b, we'll put it thus, as I usually do. So thus, we're going to have integral from a to b of f of x gx dx is going to equal to, well, we're going to have a value f of c, an intermediate value between the maximum and the minimums, and times it by integral from a to b of g of x dx. So there it is. And there's our proof. And again, where c is between a and b. And let's just circle this. There it is. This is exactly the proof. And you can scroll above. Yeah, we can scroll above here to the theorem. So here's theorem, integral from a to b of fx gx times dx equals to f of c times integral from a to b gx dx, where c is between a and b, and g of x does not change sign. And then we chose g of x as positive. If it's negative, we're going to have, it's going to be the exact same thing, but I'm just going to move around these inequalities. You can move it around, so the maximum is going to be, this one's going to be, this side will be the minimum, this side will be the maximum, but nonetheless, it's still going to be true, because we're still going to have the exact same thing as the intermediate value theorem is a value in between that. in between the minimum and maximum. So anyways, this proves the weighted mean value theorem, and now we're going to use that to prove theorem 3, which is Lagrange's form of the remainder term. So if the n plus 1 derivative of f is continuous on an open interval I that contains a and x is in I, then there exists a number c between a and x, these are all in I, the open interval I, such that, and we can write this out as the Lagrange's form of the remainder term, Rn of x is equal to f n plus 1. Again, yeah, so this is not going to be an integral, so it's simpler than the previous version. So the n plus 1 derivative at c, divide this by n plus 1, absolute value, yeah, I mean the factorial, n plus 1 factorial, times it by x minus a to the power of n plus 1, like that. And yeah, here's we'll make a quick note before I go to the proof. So note, this is an extension of the mean value theorem. This is for derivatives, which is the case n equals 0. So when you have n equals 0, so at n equals to 0, what we're going to have is we're going to have r of 0 of x, like that, equals to this fn 0 plus 1, that's just going to be the first derivative at c, and then divided by 0, like that, 1 factorial, and here's going to be x minus a. This is going to be x minus a to the power of 0 plus 1. So in other words, this is equals to f of c times x minus a. So this is just an extension of the mean value theorem. This is just a mean value theorem one. As you scroll above here, so scroll all the way up. So remember the mean value theorem. If it's continuous on, that's extreme value theorem. So here's the mean value theorem number here. See, we had f of c, f prime of c is equal to f of b minus f a divided by b minus a. Move that around. So we get this part here. F prime of c times b minus a. So yes, and this one here is that R0 could be considered. But anyways, just an extension of that mean value theorem for derivatives. So yes, very interesting part. I'll just circle this part there. Alright, so now let's look at a proof for this theorem 3 right here. And what we'll do is first note that the function g of t equals to x minus t power of n doesn't change sign in the interval from a to x. So we're going to be looking at this, but from a to x, there's replace it with t. And also just look at the power of n right now instead of n plus 1, but we'll get to that soon. So this function, g of t equals x minus t power of n, doesn't change sign from a to x. That's because when you plug in the maximum value x right here, that you can get is 0. And when you're subtracting x minus a, where again a is, if you look at the theorem is from between a and x. So a is less than or equal to x. Yeah, so then this doesn't change sign. It's always going to be positive or negative if x is negative. Yeah, so the weighted mean value theorem, the weighted mean value theorem for integrals gives a number c between a and x, such that, and again, let's just scroll up to the mean value theorem. So we have right here f of x, gx, dx, and this one is this is f of c, and this is g of x. So in our case, we're gonna have g of t like that, and we're gonna take the integral from a to x. We're gonna go from integral from a to x of, and I'm gonna write this as f of t. Yeah, f of t. This is gonna be g of t dt. This equals to, and this is gonna be equal to f of c, and you're just writing everything in terms of t. The integral from a to x. This is g of t dt, and just to see this again. So yes, this is exactly this one here. Instead of x, we're doing t because we're evaluating it from a to t. I mean a to x. So f of c, this is g of x again. So integral, and this is f times g. So this is what we have. And now this case right here. So this one right here is our. So assume this is x. This is equals to x minus t to the power of n. And the reason is the power of n is because we're going to take the integral right here to get an n plus 1. So you can see what we'll do with the proof. And now this fn plus 1 of c, so we're going to plug that in as this. So this f of t is equal to, we're going to replace that with fn plus 1 of t. So that it matches up with this right here. So that we have fn plus 1 and of c like that, to get that over to this side. So in other words, what we're going to have is this gets replace all the terms. So a to x of n plus 1 of t, and then g of t is going to be x minus t. And this is going to equal to, well, f of c, f of n plus 1, yeah, so we're going to replace that like that, of c, times it by, and also forgot to include the dt over here. This is going to be dt. This equals 2, and now integral from a to x of x minus t dt, the power of n, times dt, like that. Alright, so now that we have this side over there, let's just evaluate everything that we can. So this is n plus 1 derivative at c of f, and this is going to be, now evaluating this, is going to be x minus t, like that. Power of n, this is going to be divided by n, this will be plus 1. Which is the integral, so we need to both of them be plus 1. So this is power of n plus 1 divided by n plus 1, because remember, we take the derivative to get the from the antiderivative. This is the antiderivative. We multiply that inside, n plus 1 cancels, or subtract 1, get over there. And also by chain rule, we're going to have a negative. So this is a negative t there, so the derivative of negative t is negative 1. Let's put that like that. This is negative. And this is going to be from a, from t equals to a, not x. So t equals to a, and t equals to x, like that. And then what we're going to get is, this is going to be f of n plus 1. This is the of c, like that. And then over here, plug in x, that goes to 0. So this is going to be negative 0. And then, yeah, so this is when you plug in x. And now we subtract this by, a negative there is going to be positive. And then we plug in a inside. So we're going to have an x minus a to the power of n plus 1 over n plus 1 bracket, like that. So that's what we have is f of n plus 1 derivative. This is the n plus 1 derivative of f at c. This is going to equal to, multiply that by x minus a, like that, over n plus 1. Power of n plus 1, like that. So that is what this integral equals to. I'll just box this out right here. We'll need it soon. Alright, so now that we have this, and now let's scroll up now, and now by theorem 1, because if you notice something, this right here, integral from a to x of fn plus 1, a derivative of f at t times x minus t divided to the power of n dt. Let's scroll up all the way back to theorem 1. See how far we can go back. Yeah, so scroll all the way back here, it's teleported here. So remember theorem 1, which we proved way earlier. This is the remainder term right here. Yeah, Rn of x equals to 1 over n factorial times by the integral from a to x of x minus t of f to the n plus 1 derivative of f at t dt. This is exactly what we just have. Now we just have this. Yeah, we just add this 1 over n factorial to the term that we had earlier. So let's just take this formula and let's just copy and paste it. So I'm just going to copy and paste this, like that. Alright, so here, just teleport it back here, and let's just paste this over, and so just paste it normally. So just paste that here. So this is from theorem 1, just copy and paste that. And notice what we have here. This is exactly this integral right here, integral from a to x of fn, this n plus 1 derivative is n plus 1, like that. And then we have of t, and this is x minus t to the power of n. And it's x minus t to the power of n. Yeah, I should have moved it over to the other side. But anyways, now we have that scenario. So we know that this, so let's put an arrow, this whole thing equals to this. Yeah, this is like that. So this equals to 1 over n factorial. And then there's n plus 1 over there, times by this n plus 1, like that. And then multiply this by fn plus 1, and this is going to be at c, times it by x minus a over n plus 1, like that. And notice here this n plus 1 times this n factorial, that's just going to equal to n factorial, n plus 1 factorial. Combine this all, write this in a compact form, n plus 1 derivative of f at c, divide this by n plus 1 factorial, times it by x minus a, like that, n plus, to the power of n plus 1. And now what we have is, this entire thing, like that. And this is exactly our theorem 3. Let's scroll up to theorem 3. So Rn of x equals to Fn plus 1 at c, and then divided by n plus 1 factorial x minus a to the power of n plus 1. And that's exactly what we just have. Let's do some check marks over there. Alright, yeah, so now the formula for the remainder term in theorem 3 is called the Lagrange's form of the remainder term, just for convenience. So yes, that's this right here. And notice that this expression, this one right here, I'll just write this down again. Rn of x is equal to Fn plus 1 c, like that. And this is n plus 1 factorial. This is x minus a power of n plus 1. Just write that down. Yeah, this expression is very similar to the terms in the Taylor series, except that we have the n plus 1 is evaluated at c instead of a. So just to recall the Taylor series. We have Tn of x, this is instead of n plus 1, equals to, right here, from infinity, n equals 0 to infinity of Fn, like that, at a over, this is n factorial, and this is going to be x minus a, like that. This is n. And you can just replace everything with n plus 1 just to get it the exact same form, or let's see if we can do this n plus 1 just to show the exact same thing, equals to, let's do n plus 1 equals 0, evaluate it from infinity up to, this is Fn plus 1 of a, just to make the exact same expression, x minus a, n plus 1 over n plus 1 factorial. And yeah, so just notice here, so we have this exact same expression there instead of here. So instead of c, like that. Circle that. There we go. And yeah, just put that a bit better. So instead of c, just put this this e a bit better. Instead of c. So now all we can say about the number c is that it lies somewhere between a and x. Again, by intermediate value theorem. That's all we know. So yeah, that's it for this this derivation. Very, very interesting stuff. Alright, so now let's go forward and do an example to illustrate this. So in the following example, we show how to use Lagrange's form of the remainder term as an alternative to the integral form in example 1, and it's the same function sine of x. So example 2, prove the Maclaurin series for sine of x represents sine of x for all x. In other words, prove the Maclaurin series for this sine of x is actually equals to the function for all x. So solution using the Lagrange form of the remainder term with a equals 0, because we're dealing with Maclaurin series. So we could just look above here. So remember, this is the Rn, this is the Lagrange form, and we're just going to plug in a equals 0. So what we'll have is, we're going to have r sub n of x. The remainder is going to equal 2, and we need to make sure this, so we need to see if this approaches 0 as n approaches infinity, and thus it will equal to sine of x. So what right here, this is Fn plus 1, yes. So we're going to have this is n plus 1 derivative at c as opposed to a. This is divided by n plus 1 factorial, and it's going to be times it by x minus a, where a equals 0, so that's just going to be x to the power of n plus 1. And where this function, this f function, so f of x is equal to sine of x, and c lies between a equals 0 and a equals, from a equals 0 to x. Actually, better to word it just here. So where c lies between 0 and x, where a is equal to 0. So, and also we know that the n plus 1 derivative, or derivative of this fx at any value c, at any value x or c, doesn't matter, is always going to be plus or minus sine of x, or in this case sine of c, or plus or minus cosine of c, as we showed in example 1 when you took the derivatives in 2 columns. When we set 2 columns, one's a derivative. So basically, actually, both were derivatives. One had the values inside. So yeah, so we know that the Fn plus 1 derivative at c is going to be either plus or minus sine c or plus or minus cosine c, but in any case, the absolute value of that derivative is going to be less than or equal to 1, because this is sine and cosine. Those are always going to be between 1 and negative 1. So absolute value is going to be less than 1. So in other words, what we're going to have is the absolute value of this remainder, absolute value of r sub n of x, is going to equal to, we just put this absolute value inside the whole thing. And so it's going to be absolute value of n plus 1, like that, of c. And well, since the bottom one is always going to be positive, is n plus 1 factorial, we could just leave the absolute value sign out of there, just put it over this one, and then also put it around this one right here, absolute value of x n plus 1, like that. So everything is always positive. So now this one right here, this is less than or equal to 1, this derivative. So in other words, this is going to be less than or equal to, just make that equal to 1, and it's going to be less than or equal to absolute value of x, put the absolute value inside, and it's going to be plus 1. So because the x is the only thing that could be positive or negative. And then this is going to be divided by n plus 1 factorial. And this form right here is the exact same as that equation 1 from my earlier video referenced earlier. So by equation 1 referenced earlier from my earlier video, the right side of this inequality approaches 0 as n approaches infinity. So this absolute value of this remainder is also approaching 0 by the squeeze theorem as in example 1. So exactly the same thing. So we just made it so that's the same formula. So it follows that the remainder Rn of x without the absolute value sign is also approaching 0. If the absolute value is approaching 0, then even this, whether it's positive or negative, is still approaching 0, as n is approaching infinity. So sine of x is equal to the sum of its Maclaurin series. So yes, very similar to above, but this one we got to here very quickly without that integral. Alright, so now let's look at one more example for end this video. So example 3, it states part A, approximate the function f of x equals to x to power of 1 over 3, or the cube root of x, by a Taylor polynomial of degree 2 at a equals 8, and then part B says how accurate is this approximation when x is between when x is between 7 and 9, or 7 is less than or equal to x and less than or equal to 9. So let's look at the solution. So part A, well, let's just differentiate. Yes, differentiating and creating two columns we have because we want to approximate this function by Taylor polynomial of degree 2. So let's get that up to speed. So let's get up to degree polynomial 2. But actually, we're going to take the derivative up to the third degree because we're going to, for the approximation, recall for the approximation, we need the n plus 1 derivative. So we want the degree 2 polynomial, we need to approximate with the degree 2 plus 1 or 3. So what we'll do now is differentiating, creating two columns. We have f of x right here. This equals to, again, this is, you could write this as x power of 1 over 3, or 3 over, this is the cube root of x, which is equals to x 1 over 3, like that. Alright, here, just moved it over there just to get some more space. And now, if you take the derivative, and also before we get that, let's just plug in the value inside here. So f of 8, because this is going to be at a equals 8. So remember, Maclaurin series a equals 0, so here is a equals 8. So we're going to plug in that for the Taylor series. We need that. So f of 8 is going to equal to 8, 1 over 3, which is equals to, remember, this is just 2 times 2 times 2 gets 8. This equals to 2. So now, yes, in other words, yeah, this is the cube root, so a number times itself 3 times. It has to equal to this 8, so 2 times 2 times 2. And now take a derivative of this, f prime of x is going to equal 2. This 1, 3 goes down. Then x minus a 3 over 3, or a 1, which is going to be negative 2 over 3, like that. Then when we plug this inside, we're going to get, so I'll move this a bit closer here. We're going to need some more space. So this is going to be, now it's going to be f prime of 8 is equal to 1 over 3. This is going to be 8 to the power of negative 2 over 3. Now this equals 2, just to simplify it to get in a form we can easily calculate. So this is going to be 1 over 3, and then put this at the bottom. This is going to be 1 over 8 to the power of 2 over 3, or you could just put this 2, leave it over here just to make it a bit easier to see. So we take the 2 out, so it's still going to be, so when you multiply this inside, it's going to be 8 over 2 over 3. But here's going to be the power of 1 over 3 like that. 1 over 3. And now this 8 to the power of 1 over 3, that's just 2. So this is just 2. So that this is going to equal 2. And let's just see if we can fit this all in. 1 over 3 times it by 1 over 2 over 2. So 1 over 2 squared, which is going to be 4 times 3. Yeah, here it's moved everything over. Let's write this a bit neater. So 1 over 3 times 2 over 2, which is 4. 4 times 3 is just 12, so it's going to be equal to 1 over 12, like that. So yes, that's what we have over there. Just fit that all in. Now we keep going. So f double prime of x So this is because we want the degree 2. So we're going to get up to degree 2, and then afterwards, then plug in for f double prime at a equals 8. And then afterwards, we'll just take a derivative at the third one, but we won't plug in a because this one is value c, so not value a. So, and that's the n plus 1. So anyways, let's just write this here. This is going to be 1 over 3, but then this negative 2 goes there, so let's put this 1 over 3. This negative 2, just put the negative. It's going to be 2 over 3, like that, and then this is going to be multiplied by x minus 2 over 3 minus the 3 over 3, that's going to be minus 5 over 3, like that. Alright, and simplify this further, this is going to be a negative 2 over 9 times by x to the negative 5 over 3. And now this one right here, this f double prime of 8, this equals 2, let's plug this all in, it's going to be negative 2 over 9 times it by x, which is 8 over negative 5 over 3. And now this equals 2, when we could have this over here, this is going to be a negative 2 over 9. Bring it at the bottom, it's going to be 8 over 3, 8 over 5 over 3, or better yet, we'll just replace this with a 2, so that this is going to be 2 to the 5. Because remember, this 8 over 1 over 3 is this part right here. That's going to be the same thing above there. So in other words, we just got to this point here, but now instead of 2 to the power of 2, we have 2 to the power of 5. And now this is 2 to the power of 1, so this would cancel. With it here, we're just left with a 4. So this 4 right here, this is 2 to the 4. This equals to, well, 2 to the 2 times 2 to the 2, which is just 4 times 4. Which equals, remember, you add these powers up. This is going to be 16. 4 times 4 is 16. And then when you multiply by 9, so what we'll have is 16 times 9. Just do some multiplication. 9 times 6 is, well, 9 times 5 is 45. This is going to be plus 9, so 54. So 4, put it 5. 9 times 1 there is going to be 9 plus 5 is going to be 14. So this equals to negative 1 over 144. So yes, just want to do exercise and calculations by hand. So let's box this out like that. And then lastly, let's just take the derivative here, f triple prime of x for the n plus 1 for the remainder approximation. So what we'll have here is, this is a negative 2. We're going to bring this negative 5 down, which is going to be negative, which is going to be positive 10. And then, 2 times 5 is 10. And 3 times 9 is 27. And it's going to be x, and this is going to be x minus, then a 3 over 3. So negative 5 over 3 minus 3 over 3 is going to be negative 8 over 3. Like that. And yeah, so we have this part here. And we don't need to take a inside, put 8 inside, because this is for the value c for the remainder. So number is n plus 1, put a c. So let's just keep going now. Alright, so thus the second degree Taylor polynomial is, and we need to approximate this by Taylor polynomial degree 2. So this one's going to be t2 of x is going to equal to, and I'll write this as the summation up from n equals 0 up to 2 instead of infinity. That's because it's Taylor polynomial, not the full series. And this is going to be fn of 8, which is our a. Divide this by n factorial, and now we have a x minus 8 to the power of n. And in our case, we're going to have a f of 8. Yeah, so the first one at n equals 0, we just get the f of 8. Because 0 factorial and the power of 0 is just going to be 1. And here 0 is just the first function. And then this is going to be now plus the first derivative at 8 over 1 factorial, just for completeness. And it's going to be x minus 8 to the power of 1. And then afterwards, it's going to be this. So that, we just need to do degree 2. So up to here, degree 2. This is going to be at 8 divided by n equals 2, which is 2 factorial. And it's going to be x minus 8 to the power of 2. And now if we plug in our values, f of 8, we know f of 8 is just 2. So this is going to be 2 plus, and then f prime of 8 is 1 over 12. So we're going to have a 1 over 12 right here. This is 1 over 12. This is going to be x minus 8. And then lastly, f double prime of 8 is going to be negative 1 over 44, but there's also 2 factorial, which is just 2. So multiply that by 2, that's just 288. So it's going to be minus 1 over 288 x minus 8 power of 2. Alright, so now that we have this, so the desired approximation is, this is the Taylor polynomial, so we're approximating it with a Taylor series, so the cube root of x, like this, yeah, of x, or x equals the power of 1 over 3, so we're going to approximate as approximately this Taylor polynomial of degree 2. T2 of x equals to, which just equals to 1 over 12 x minus 8. So just put this for completeness, put it all down. 2 over 88 x minus 8 power of 2. And now part B, which is how accurate is this approximation when x is between 7 and 9. So what we'll do is, well, let's use the Lagrange form of the remainder term. We can write, remember the Lagrange form is just over here, Rn of x equals to fn plus 1 derivative of f at c, and then n plus 1 factorial, and this is x to the power of n plus 1. Actually, I mean, no, this one is for the Maclaurin, that's for a equals 0. So remember, it's just x minus 8 to the power of n plus 1. So let's write down this Lagrange form. So we're going to have Rn of x is going to equal to, this is going to be fn plus 1, the n plus 1 derivative of f at c, divide this by n plus 1 factorial, and now what we're going to have is a x minus 8 power of n plus 1, like that. But in our case, our n is equal to 2, so we'll just put this 2 like that, and to approximate it, we're going to get a 2 plus 1 is 3. So let's just let's just write this separately. Actually, just leave it like that. So we're going to have, for our case, r2 of x is equal to f of 3, and that's why I took the third derivative, or else put f triple prime like this. So f1, 2, 3 of c over 3 factorial, and now we're going to have a x minus 8 to the power of 3. And remember f triple prime of c, this one is, well, we know this derivative is 10 over 27 times x to the power of negative 8 over 3. So in other words, this is going to be equal to 10 over 27. Then this 3 is going to be 3 times 2 is 6. Or better yet, just put this as 3 times. Just put this as 3 times 2, so that we can cancel this with, put it at 5. This becomes a 2. Yeah, the 2 cancels, and then this is going to be c to power of negative 8 over 3, because that's for we'll plug in c inside here. So negative 8 to the power of 3, and then times this by x minus 8 to the power of 3, like that. Alright, so now continuing further, this equals to, just simplify it all, it's going to be 5 over, and then 27 times 3, number 27 is just, this is just 3 times 9. So in other words, when we have 3 times 9 there, and this is times by 3, this is going to be 9 times 9. 3 times 3 is 9, so that's just 81. So all equals 81. So this equals to 5 over 81. And then times it by, and I move this at the bottom so to get rid of the negative power. So what we'll have is c to the power of 8 over 3, times it by x minus 8 to the power of 3, like that. Alright, so we have this, now let's just box this in, and we have it to go. Like that. Yes, now that we have this error in this form, and now where we know that c lies between 8 and x. Yeah, as per the Lagrange's form of the remainder term, so as in Theorem 3. So in order to estimate the error, we note that, well, x is between 7 and 9, then what we'll have is, well, what we'll have is, so we'll have an x like this. This is greater than, yeah, put this like this. X is greater than or equal to, and put a 7 across there, less than or equal to a 9. And what we'll do is subtract 8 on all sides. Minus 8, minus 8, minus 8. So in other words, what we'll have is, so that we have this x minus 8 over there, so we can see what value it's going to be in between. This is going to be equals to 1, this equals to negative 1. So in other words, what we'll have is x minus 8 is less than or equal to 1, greater than or equal to negative 1. In other words, the absolute value of x minus 8 is going to be less than or equal to 1. So what we'll have is absolute value of x minus 8 is less than or equal to 1. Also, now that we have this inequality, the next step is, well, we know that since c is greater than 7, that's because c lies between 8 and x is going to be greater than or equal to 7 and less than or equal to 9. So in between that, the lowest it can be is x could be 7, but c is in between that from 8 to 7. So c is always going to be greater than 7 because it's again in between x and 8. So what we're going to have is c. So what we have here, this value here. So we have now this x minus 8. Yeah, we have this x minus 8 inequality, and now we'll look at this inequality, this c to the power of 8 over 3. So c to the power of, let's write this a bit better. C to the power of 8 over 3. This is going to be greater than when we have 7 inside. So 7 to the power of 8 over 3 when c equals 7. And this is equal to, if you plug this into the calculator, you're going to get something like a 179.306, which is, well, greater than 179, just to round up. Yeah, greater than 179, just box this in. Alright, so now that we have this, and also here's just a calculation check for my OneNote, so 7 to the power of 8 over 3, let's just delete this and show, equals, yeah, so about, and it just rounds up to 306, like that. So what we have now is, and I'll just remove this decimal place, this period. So what we'll have is, when you look at this remainder term, so R2 of x, so let's write this down. So R2 of x, which equals to 5 over 81, is equals to 5 over 81 times it by c to the power of 8 over 3. Divide this by, divided it by into x minus 8 to the power of 3. Yeah, and so this remainder, but here we'll take the absolute value of it, and also this absolute value. So then the only thing that can be negative is this x minus 8. So leave it like that, absolute value. And lastly, I forgot to include over here. Yeah, so here, this point here, we have this absolute value of x minus 8 is less than 1, like this. But this is the same for when you take the power of 3. Then when you take the power of anything between, the maximum is still going to be, so I'll put thus. Maximum of the x minus 8 power of 3 is also going to be less than or equal to 1. The highest it could be is if it's 1, then power of 3 is just 1. If it's anything below, you're going to get lower value than 1. Yeah, so that's what we'll have is a maximum. This could be just going to be less than or equal to. I'll just put a less than. And yeah, just put a less than, because here we're rounding up this 306, and this is going to be 5 over, we're rounding down, You're rounding down to 179, so what we'll have is, less than, and again, we're dividing by a small number there for the c, but in any case, less than or equal to it, doesn't matter. Let's put it less than this, we want this error less than this, and this is going to be x minus 8 times 1. So it's less than, times 1, this one's going to be 79, like that. And if you plug this into the calculator, what you'll get is a 0.000, 3 zeros, and something like a 345 rounded up. And then this is, well, less than 1. Less than, this is going to be less than, and my calculus book just rounds up all the way to 4 to be very conservative. So less than 0, 0, and then 4, like that. So that is our error. And here, quick calculation check. So from here, from my calculus book, so 5. from my OneNote, so 5 divided by my OneNote built-in calculator. So 5 divided by 81 times 79. This equals to, well, this doesn't get that accurate. It gets it to, it gets it just to the 3 there. But if you plug into another calculator, it'll go up and then round it up to 345, like that. But anyways, this is a double check. So this is gonna be less than 0004, and this is what the notes or the calculus book, the additional topics PDF is saying, just goes up to 4. So anyway, so thus if x is between 7 and 9, the approximation in part A is accurate to within 0.0004, 3 zeros and a 4. To be conservative, there's a 345 there, but just stick with the 4. Anyways, that is all for today. Hopefully you followed along. And this is another pretty epic video, another epic long MES math video. But I find this is a great way just to get my brain up to speed and learn a whole bunch all at once. And the making of this is pretty intense too, just to make sure everything is compact, nicely written, and And yeah, nice follow through format. Anyways, that is all for today. Like always, you can download these exact notes in a link in the description below, as well as viewing these notes on Steemit. And yeah, that is all for today. Thanks for watching, and stay tuned for another Math Easy solution.